Hello Year 10s, Mrs Elliott's hand again. This time I'm just going to go through the 3 questions that seem to cause the most problems with the online skills test that you did on chapter 15 on Caboodle. So they were all to do with sort of volume, sort of shape and space type questions. So it was the last 3 that caused the most problems, and I think it was because they were dealing with similar shapes, okay? And I think a few of you have forgotten how to do similar shapes questions. So this was the first one, so I've just written it out. A tank is in the shape of a hexagonal prism. The area of the base is 16 meters squared. A similar tank, and I think that's the thing that you really need to watch out for on these questions. They don't just mean similar in the sense that it's part of the English language to use the word similar. They're using similar very specifically to refer to the mathematical term. So a similar tank has a base area of 4 meters squared and can hold 8,000 litres of water. How much water can the larger tank hold? Now, I usually tell people to draw a diagram at this point, but hexagonal based prisms are a bit difficult to draw. They would sort of look like this, and I'd make a complete hash of it. You don't really need to have anything like that here. You just need to think about areas and volumes, okay? So for any prism, regardless of the shape of the base, so here's a hexagon shaped base, the volume of it is the base times the height. If we've got 2 similar ones here, one is just going to be a bigger version of the other, okay? So there's my really rubbish sketch of a bigger hexagonal base prism. Doesn't really matter, you don't really need the diagrams here, okay? What you do need to think about are the areas. So area of the smaller one, or the smaller base, is 4, and the area of the larger base is 16 meters squared. Now, remember our rules about similar shapes when they're in 3 dimensions. Our scale factor going from 4 to 16 here, the scaling up going from the little tank to the bigger tank, is an area scale factor. So our area scale factor is going to equal 4, yeah? 16 divided by 4, or 4 times 4, however you look at it, the area scale factor going from the smaller one to the bigger one is a 4. Yeah, you could do it the other way around. You could go from the bigger one to the smaller one, but I'm going from the smaller one to the bigger one. Okay, so I've got an area scale factor of 4. Now, if I want to know something about the volumes of these 2 shapes, remember this one had a base of 4 and a volume of 8,000. I'm going to need, this one had the base of 16, and the volume we don't know. I am going to need a volume scale factor. Now, I can't go straight from an area scale factor to a volume scale factor. If you think about it, if a scale factor is K, do you remember we used K? Then our area scale factor is K squared. If our area scale factor is K squared, then our scale factor is K. And that means in this case that our scale factor is going to be the square root of 4, which is going to be 2. Yeah? Our volume scale factor, volumes are measured in cubed units. So our volume scale factor, if you remember, therefore is going to be K cubed. K cubed is going to be 2 cubed, which is 8. So we can apply our volume scale factor to the volume of our smaller tank. Our smaller tank has a volume of 8. So our larger tank volume is going to be that 8,000 multiplied by the volume scale factor of 8, which gives us 64,000, and what are we measuring in? Meters cubed. So this is all about remembering that you can, for similar shapes, you can scale them up and scale them down, as long as you know one measurement that is this measuring the same thing for both of them. So in this case, we knew that our base area of one was 4 and the base area of the other one was 16. That allowed us to get to an area scale factor. From our area scale factor, we can get back to a basic scale factor just by square rooting it. So I've lost the ability to speak. And from a scale factor, we can scale up to a volume scale factor by cubing. Yeah, and then our larger tank volume will be the volume of water. Oh, it isn't in meters cubed, it's in litres. Will be our volume of water in our smaller tank. And multiplied by our volume scale factor. Yeah. The next question deals with scale factors again, so we'll have a look at that as a reminder. So that was question 8. So if you need to pause for a second just to make a note of that, I'm about to swap the question over. So pause if you need to just copy anything down from that. Okay, so question 9. Here's one I prepared earlier. It's just like Blue Peter here. I might be lost on some of you who are a bit too young for Blue Peter. There you go. Right. So A and B, in this case, are two similar cylinders. The volume of A is 69 centimetres cubed. What is the volume of B? Now, they don't tell you in the text any other measurements, but on these two shapes, we are told their heights. We are also told again that they are similar shapes, okay? So we know that this one has a height of 5 and this one has a height of 15. They're similar shapes, so one is an enlargement of the other, though we are working in 3 dimensions. So what we need to work out from our height and our height is a scale factor. Because it is just relating to a height, it's just going to be a linear scale factor, yeah? So our linear scale factor is going to be what we need to multiply the 5 by to get to the 15. So 15 over 5 is 3. And remember, that's our k. That's what we do to multiply. We're multiplying by k. That's our linear scale factor to get from a height, or it could have been a radius on this one, to the same measurement on that one, the corresponding measurement on that one. Now, we're interested in volumes. We're told the volume of A is 69 centimetres cubed. That's this one here. 69 centimetres cubed is the volume. So we need to work with a volume scale factor to scale up that volume to get to this volume. So we say our volume scale factor, which remember is going to be a cube of the original linear scale factor, is going to be 3 cubed in this case, which is 27. Therefore, to work out the volume in cylinder B, volume of B, we take the volume of A and we multiply it by that volume scale factor. So the volume scale factor is going to be 69 times 27. Sorry, not the volume, it's the scale factor, just the volume, and that's 1863. 1863, and we are measuring in centimetres cubed. Okay, so that was question 9. Again, I'm going to take it away in a moment. So if you need to pause at this moment just to take a few notes, then do so. The principle again is to do with the similar shapes. Yeah, we've got to remember that we look at our two shapes that we've got. If we're told they're similar, that means they're mathematically similar. And we should be given either in the text or on the diagram, as in this case, we should be given 2 corresponding measurements. In this case, those corresponding measurements were both lengths or heights. And because we've got those, because they're heights, they give us a linear scale factor, or we can use them to give us a linear scale factor. If we'd been given areas, we would have found an area scale factor, which is what we found in the last question. And if we've got volumes, we could have found a volume scale factor. You use those to get to a linear scale factor, and then you use that to find whatever it is you need in the question. In this case, it was a volume. Okay, final question, slightly harder one. So the final question, I'm just going to make sure I've lined this up on my camera. Use my laptop. I'm just going to make sure I've lined it up so that it actually works. I'm just going to, there we go. So we've got a frustrum, and I've upped out the frustrum, so I have to put it on again. Hang on a sec, I'm just going to go to my, so my frustrum from the question, I'll pop it on here, has these dimensions on it. The base of the frustrum, now remember a frustrum, this is 4.5, this is 4, and this is 3, and they're all in centimetres. Remember that a frustrum is basically the bottom part of a large cone that has just been chopped off. So a little cone has been chopped off the top of the bigger cone. So I'm now going to draw that in. Okay, so here's my bigger cone, and I'm just going to draw a line sort of halfway, well not halfway, but a certain distance up, so you can see how this frustrum was formed. It was basically a bigger cone that's had a little cone taken away from the top. So I'm going to put my measurements back into this one, and we're going to use this one for our working. So I know that that's 4 centimetres there. I know that I've got a 4.5 centimetre radius for the base of the big cone. And for this little cone on the top here, I've got a 3 centimetre radius. Now, what you need to remember on these sorts of questions is that this bigger cone is just an enlargement of this smaller cone. Therefore, the smaller cone and the bigger cone are similar. If they are similar, which we know they are, so I'm going to write that down here. Small cone and big cone are similar. That means that if we've got a corresponding measurement for those two cones, we can work out a scale factor, be it a linear scale factor or a volume or area scale factor. Now we do have a corresponding measurement here. We're going from 3 on our small cone radius to 4.5 on our large cone radius. We can therefore work out, because this is just a linear measurement, we can work out our linear scale factor. So our linear scale factor going from the small to the big, which is what I usually like to do because it gives you numbers that aren't fractions. Having said that, this is going to be a, but it gives you larger numbers, is what I should be saying. Our linear scale factor to go from a 3 to a 4.5 is 1.5. So 3 times 1.5 gives you 4.5. So that's our linear scale factor. Now we are trying to calculate the volume of this frustrum, so we will be working with volumes, yeah? So overall, our volume is going to be dictated by the measurements that we've got here. Now, looking at this, if we want to calculate our volume just of this bottom section, the way to do it is to take the volume of the big cone and subtract from it the volume of the little cone. I'm going to write that down. So volume of the frustrum equals volume of big cone minus volume of little cone. Or you could take the volume of the big cone and you could divide it by a volume scale factor, which would be 1.5 cubes. You could do it either way. I'm just going to do volume of big cone minus volume of little cone because I think it illustrates the point quite nicely. We could just do a side working in a moment to make sure it works the other way as well. Now, if we're going to work out the volume of the big cone, which we've got to do for either of those calculations, we need to know what the height of the big cone is. And at the moment, we are missing that height. So I'm just going to put in an extra measurement in there. And that extra measurement in there takes me to the full height of the bigger cone, okay? And I am going to use what I know about these scale factors to work out what this x is, and thus what the whole height is going to be, okay? So, missing height. So I know that the height of my overall big cone here, so is going to be, so height of cone, height of big cone, I should write, equals x plus 4. But I also know that the height of my big cone has got to be 1.5 times the height of just the little cone, yeah? So my height of my big cone is x plus 4. I know that from my diagram, but I also know that that's 1.5 times the height of my little cone. See how that works? So that means that I can solve this little equation. If I take away x from both sides, 4 equals 0.5x, divide by a half, 8 equals x. I now know this measurement here is 8. So I've now got a height for the overall big cone. The overall big cone height is 8 plus 4, which is 12. I know the height for my little one is 8. I've now got all that I need in order to be able to calculate the volume of my frustrum. Now, as I said, I'm going to do this in two ways. So I'm just going to do the big height minus the big cone minus little cone version over here. So big cone minus little cone volume to get my frustrum. So my big cone, remember the volume of a cone, I'm just going to write using 1/3 pi r squared h. That's my formula, isn't it? 1/3 pi r squared h is the formula for the volume of a cone. So for my big cone, I've got 1/3 pi times my radius is 4.5 squared, and h is 12. I'm going to take away the little cone's volume. That's 1/3 pi. My radius of my little cone's base is 3, and my height is 8. Right, I'm going to put that into a calculator. So I've got 4.5 squared times 12. So this is 81 pi. Just going to check that again. 4.5 squared times 12 divided by 3. Yeah, that is right. Just didn't seem right. This was 9 times 3 is 72 divided by 3 is 24, minus 24 pi. 81 minus 24. You can hear me typing. I don't quite trust myself on my calculator or on anything really at the moment. Lockdown isn't doing a lot for my mathematical skills. Oh, and that gives me 179.1, but I'll just go for 179. And what am I measuring in? Centimetres cubed. So I've calculated my volume of this base, the frustrum, by doing the volume of the big cone minus the volume of the little cone. Now, I said there was another way of doing it, and the other way of doing it is still using the volume of the big cone, but using the volume of the big cone and the scale factor for volume, the volume scale factor. So I can calculate the volume of my big cone. My volume of my big cone is 81 pi. I've still got to take away my little cone from that. So my little cone in this case is going to be my 81 pi, volume of my big cone, but it's going to be divided by my volume scale factor, 1.5 cubed. Yeah, so 81 pi stays, hopefully. 81 divided by 1.5 cubed, that gives me 24 pi. Same as this one here, yeah, which is 179 centimetres cubed. So that was the only difference really in those workings, so it's only used right at the very end, was how I calculated the volume of this smaller cone. So I calculated that smaller cone volume by taking the bigger cone volume and dividing by the volume scale factor. My linear scale factor was 1.5, so my volume scale factor was going to be 1.5 cubed. Don't necessarily need to use that method, just understanding that one is important. The idea of understanding the big cone minus the little cone is, knock that off, is the main thing with understanding how frustrums work. So hopefully that's nice and clear now, and you can always email me or email your maths teacher if you have an issue with it. Okay.